Um, so I'm Jesse, and I'm presenting Timestamp as a Service, not an Oracle, which was published in VLDB this year by some Alibaba engineers. An Oracle is someone who speaks for a god and reveals divine knowledge. And in computer science, we use the term Oracle for uh, a machine that can do something impossible, like solve the halting problem or generate truly random numbers. And also, for some reason, we use the term oracle for timestamp oracles, which are um, just servers that give you monotonically increasing IDs when you ask for them. They're often used by distributed databases for ordering, and it's called a timestamp, but it might or might not be of time type, that it might not be related to the wall clock. The important thing is that it's increasing. You could use a Lamport clock or a vector clock instead, but that requires you usually to pass these clock values back and forth between databases and clients. And I know from my own experience that database users have a really hard time preserving these timestamps through all of the layers of their uh, multi-tiered architecture. You could also use synchronized clocks, but then you have to sync them, and no matter how precise they are, you still need to wait out the uncertainty. So a solution is a timestamp oracle. It's usually a single server or a single group of servers in your data center. And every time you ask it for a timestamp, it gives you an increasing value. The paper mentions that timestamp oracles are used by all of these systems. I've heard of half of them. And the TiDB placement driver, um, it does other things, but it includes a timestamp oracle as part of its implementation. So this TiDB placement driver is going to be uh, the competition that this paper uses to compare its new solution against. Timestamp oracles work for one data center. In order to use them as part of a database transaction, you need to be on a very low latency link to it. So it's really intended for a single data center. And this paper's timestamp as a service is also going to work for one data center. They're not trying to solve that problem here. For fault tolerance, the Oracle can be a consensus group. So each new timestamp is majority committed. That way, if the leader fails, the next leader will remember what was the highest timestamp given out so far so that it can give out greater timestamps. And the paper mentions that this can be optimized. The leader could majority commit a range of timestamps, and that if it fails, then the next leader will start with a new range that's strictly higher than the previous one. Even if the Oracle is a fault-tolerant consensus group, losing the leader causes some brief unavailability while we're waiting for a new leader to be elected. And then for speed and consistency, the group generally has to use leader leases. And so that increases the unavailability more because the new leader has to wait out the previous leader's lease before it can start giving out timestamps. Besides this unavailability, the other problem is that the leader is a bottleneck. You can't spread out the load by getting timestamps from followers, so a high throughput system could saturate the timestamp oracle leader and get bottlenecked on getting new timestamps. So this paper proposes timestamps as a service, not an oracle. And what do they mean by that? They say that since an oracle is one server, maybe even if it's the leader of a consensus group, that it's a single point of failure. And if it goes down, there has to be some period of unavailability, whereas they define a service as something which is not a single point of failure. I don't know if Lots of people agree with these definitions of oracle versus service, but I think it's an interesting distinction, even if these words aren't necessarily the right ones for this idea. So they propose timestamp as a service, which is a distributed algorithm that computes logical timestamps from a consensusless cluster of clocks. And this consensuslessness is not only fun to say, but it's really fun. It's the most fun part of this paper. What they mean by consensuslessness is that the servers do not talk to each other. And also, the clients here are not going to talk to each other. This is a bipartite architecture where clients talk to servers and servers talk to clients. Clients don't talk to each other. Servers don't talk to each other. There's no unavailability from the loss of a leader. We'll see that there is no leader. And there's also, therefore, no bottleneck on the leader. So how does this work? The paper presents the algorithm in two stages, starting with a simplified version. So the algorithm version 1 assumes that there are no server failures and no message loss. The algorithm can take any number of clients, it really doesn't matter. There's some number n of servers. I don't know if the paper discussed reconfiguration or not, but we'll assume that there's fixed number of servers throughout. Just curious to see the chat message 1 sec. Can't. Oh. Okay. So the client starts a session in algorithm version 1 by sending the bottom timestamp to all servers. And I'm going to call this session S. The paper generally uses sigma and other Greek letters for session names, but I don't read Greek, so I'm going to say S. And that symbol for bottom timestamp, you can think of that as negative infinity or maybe null. And whenever you see that symbol, you know that you're probably in the realm of lattices and partial orders and abstract algebra and that kind of thing. And that's going to be true here. A session in this paper is not a sequence of database commands. It's just the commands that a client has to exchange with servers to get one timestamp, and then the session ends. And the client never remembers anything from one session to the next. It always starts each session fresh. Whenever a server receives a request from a client, it increments its own timestamp. So the servers do have state. They remember the last timestamp they handed out. So the server increments its timestamp and sends its new current timestamp to the client. And the session is complete once all servers have replied. And then this is the interesting thing. The client uses the mth smallest timestamp from the replies, and it can be any m, 1 through n. The constraint is that all clients have to use the same m in order to ensure that each gets a greater timestamp. And the paper starts abstract by showing that the algorithm is correct for any m, and it spends a long time in this abstract level. Eventually, it says that for maximum fault tolerance, m should be the smallest majority. So then it starts to look just like consensus, same as a quorum in Paxos or Raft. But for now, we're going to stay abstract. We're just going to say that m is some number between 1 and n inclusive. The algorithm guarantees that the timestamp for session S is larger than the timestamp for any session that ended before S began. And this is called Theorem 1 in the paper. It sounds to me a lot like a linearizability guarantee. I think that you could maybe call, yeah, I'm not sure if it's exactly linearizability. The paper mentions linearizability, but it doesn't spend much time focusing on it. So let's look at an example from the paper of version 1 of the algorithm going. So we have a client V on the left and client W on the right. and servers X, Y, and Z have their timelines in the middle. Time goes from the top to the bottom. And can you see? You can't see my mouse. That's all right. Session alpha is on the left top, and session gamma is left bottom, and then session beta goes all the way on the right from the top to the bottom. And let's just say that M equals 2. So at the end of each session, the client chooses the second smallest timestamp or the middle timestamp from all of the server replies. So session alpha gets 1, 1, and 2. Therefore, its result is 1. Session beta gets 1, 2, and 3. So its result is 2. And session gamma gets 2, 3, 3. So 3 is its outcome. Theorem 1 guarantees that session gamma will have a greater outcome than alpha because it starts afterward, and it does. Beta could get any number. It could get, because it's concurrent with both of the other sessions. And also, we're not guaranteeing uniqueness yet. So it could get the same number as one of the other sessions. The client could send all of these messages in parallel or in any order within a session. The latencies could be of any length. It doesn't matter. The algorithm still works. So the proof of this guarantee, theorem 1, the theorem says that if S ends before T starts, where S and T are sessions, then the smallest response in S is guaranteed less than the smallest response in T. And their proof of this is a proof by transitivity. So it's 3 steps. So we say that the nth smallest response in S is less than or equal to the nth smallest server state at the end of S. We know that because server states only increase, and the client has actually heard from all M, actually all of the servers. And so it knows that all of them will have greater values, at least, or equal to as when it started. Then we take that same value, the nth smallest server state at the end of S. We say that that's less than or equal to the nth smallest server state at the start of T. We know that because S ends before T starts, and server states can only increase. Then finally, we take that value, we say the nth smallest server state at the start of T must be less than the smallest response in T, because the client talks to all the servers and it therefore increments all of their values. And therefore, by transitivity, the first value of line 1, the nth smallest response in S, is less than the last value on line 3, the nth smallest response in T, QED. The appendix of the paper has more detail about this proof. The reasoning is kind of like quorum overlap properties in Paxos and Raft, but it doesn't seem to actually require that M is a majority of N. The claim is that this works for any size of N. So that's theorem 1, assuming no server failures or message loss. And now we can go on to the second and final version of this algorithm, which deals with failures. So here the system model is that servers can crash fail indefinitely, or they can come back online, but each server's timestamp increases monotonically. So a restarted server remembers the last timestamp it produced. And the only way to guarantee this is some kind of replication for each of the servers. The paper suggests you could use RAID, or if they store their state in cloud storage like S3, S3 has its own replication and fault tolerance, or you could make each of the servers actually a consensus group. Now, if we do that, you might think that we're just going back full circle to the problem we were trying to solve. But the proposal here is if you have three different servers, then you have three separate consensus groups. So if one of them goes down for a while, electing a leader, or for some other reason, it will not cause unavailability because the clients can talk to the other consensus groups. So the servers are still acting independently and they're not talking to each other, and there's no single point of failure. Now, the goal of algorithm 2 is to find a timestamp which is greater than the nth smallest of all servers' timestamps when the session started, and less than or equal to the smallest of all servers' timestamps when the session ends, because these are the two facts that theorem 1 depends on. So we need to be sure that these two things are true, even if we can't talk to all the servers because some of them are crashed or partitioned. So here's another example of a session, but this is the algorithm version 2, where server X is partitioned away from the client. Once again, let's say that m equals 2. We want the second smallest timestamp. So the client remembers that at some point in the past, it got a 5 from server X before server X was partitioned away from it. And this memory that the client has is a new feature of the version 2.0 algorithm. So we start session delta. We get a 4 and a 5 from the servers we can reach, and we pick 5 as the timestamp for this session. And how does the client know that it can do that? Well, it knows that 5 is greater than the second smallest timestamp at the start of the session, because it knows that both X and Y started the session with less than 5, because I got 4 and 5 from them during the session. It also knows that 5 is less than or equal to the second smallest timestamp at the end of the session, because both X and Z now have timestamps that are at least 5. X returned to 5 sometime in the past, Z returned to 5 in this session. We know that their current states are at least 5. So the two facts that theorem 1 relies on are both true. So the client can pick 5 without even talking to server X. Now, in the next session, the client gets a 5 and a 6 from the service that it can reach. X is still unavailable. The thing is that it doesn't know the second smallest timestamp now, because if server X was talking to some other client in between, X might have advanced to 7. So if X has 7, then the second smallest value will be 6 out of 5, 6, and 6. Or what if server X has a timestamp of 5.5? Because timestamps don't have to be integers. And this is one of the things that I didn't like about the paper, is that it springs on us now that timestamps don't have to be integers. But if X is 5.5, then 5.5 is the smallest, second smallest out of 5, 5.5, and 6. So the client doesn't know what the second smallest timestamp is for this session, and its solution is something new. Now, instead of sending the bottom timestamp out again, it specifically sends a 6, which it thinks might be a candidate timestamp. It sends that to Y. Y does its usual thing. It increments its timestamp and returns it. And now we know that 6 is the second smallest timestamp. Server X is still down. The client doesn't care. It knows that the second smallest timestamp is 6 because 6 is greater than the second smallest timestamp at the start of the session. It knows that servers Y and Z both started with less than 6 because they answered 5 and 6 in the session. 6 is also less than or equal to the second smallest timestamp at the end of the session. And the client knows that because servers Y and Z are both now at least 6 because they replied with 6 and 7 in the session. So the client achieves certainty by advancing one of the server's timestamps without talking to the downed server. So this is one example of the algorithm, and then here's the pseudocode for the general algorithm for fault-tolerant timestamp as a service. The paper uses its own pseudocode notation, which seems hard to read for me, so I obviously made up my own pseudocode, which will probably be hard to read for you. Sorry. So for the fault-tolerant version of the algorithm, the client needs to remember all the timestamps it got in the past from each server. So it creates a map here from server to timestamp, beginning with the bottom timestamp as the initial value. And then whenever it needs a timestamp, it runs this do session procedure. And here, it's got an empty map, which the paper confusingly calls session. And this is a map from server to timestamp, beginning this time with the top timestamp as the initial value. As we saw, it sends the bottom timestamp to all the servers, and then it processes each reply as it arrives. When it gets a reply, it updates a global cache by strictly increasing timestamps. It shouldn't have to do this because servers will monotonically increase, but you could get out of order replies. So if you get a 6 and then a 5, you keep the 6. For the local session map, same thing, but now we are storing the minimum. I think this is partly just to replace the top timestamp with a actual number whenever one arrives. I think it's weird that if there's an out of order message, like you get a 6 and then a 5, you would replace the 6 with a 5. I don't think that hurts correctness, but it could require more retries, and I don't know why the algorithm works this way. We check if we received at least m replies, and we set the candidate to the nth smallest value in the session. And if the candidate is less than or equal to the nth smallest value in the cache, then we can return it. So why do we now know that this candidate is the correct timestamp? The goal was to find a timestamp which is greater than the nth smallest of all servers' timestamps at the start, less than or equal to the nth smallest at the end. We know from the session local map that at least m servers started less than the candidate because these are the values that these servers returned in the session. And we know that it's less than or equal to all servers' timestamps when the session ends because we've been tracking that in the global cache. The point of all this is to ensure both that we have a larger timestamp than the previous session and that we're sure that the next session will get a bigger timestamp too. And at this point, we've learned enough to guarantee those things. If the candidate is not less than or equal to the nth smallest in the cache, and there are no more quickly available replies, the paper is vague about when this line runs. There's probably some configurable timeout about how quickly you start retrying. But regardless, we now do something called promoting the candidate, where for every server that might have a smaller timestamp than the candidate, we send the candidate timestamp to the server to make it increment. We don't wait for its reply. We just go back up to the top of the while true loop and continue processing replies as they arrive. So I hope that that was clear. I spent a lot of time understanding this paper, and I wanted to talk for a while to share my understanding of it. The paper now gets a little bit more practical. It started by spending a lot of time not setting M to a typical quorum size, but it does a little bit of arithmetic and it says that actually M should be a quorum after all. It should be a majority because this will maximize fault tolerance. You can tolerate the largest number of down servers if you just set M to n+1/2. Section 3.3 has the details of this, and it sort of feels like it was quorum overlap all along, but the authors insist that this isn't consensus because the servers never talk to each other. Now, the algorithm that we've seen so far doesn't guarantee unique timestamps. If there are concurrent sessions, they could get the same timestamp. So the solution to that is quite simple. You just append each server's ID to the return timestamp. If servers have unique IDs, which seems easy to guarantee, then you will get unique timestamps. In their evaluation, they compare their timestamp as a service to the TiDB placement driver. And they admit that in the happy case, timestamp as a service is higher latency, especially as you add more servers. So you have to trade off latency versus fault tolerance. But on the other hand, after a leader failure with TiDB PD, it stalls for 10 seconds. Presumably it has a 10-second leader release. And they also say that in general, timestamp as a service latency doesn't increase much when servers are slow or dead, so long as the majority is healthy and M was set to a majority. My evaluation is that this paper used needlessly weird notation. These are actual pieces of notation that were used in the paper. This looks a lot less like math to me and more like some alien language. The one on the bottom means the second smallest timestamp received by session delta. And I guess that's fine, but I never explained why delta gets that upside down hat. I don't know if that's because that's some rule in this alien language. Maybe in this alien language, delta needs a hat and needs to wear it upside down because that's how aliens wear hats. And this is the language they speak. But I found the thing like really slowed down my understanding until I rewrote it for myself. Besides that, they're going to a lot of trouble to avoid the risk of brief unavailability when losing the timestamp oracle. And I was wondering if that's so bad. But then I thought, well, the oracle leader has to have a lease, and that lease has to expire after the failover. So the new leader has to wait. So maybe, yes, that risk is great enough to justify all of this effort. They have a really good evaluation section in this paper. They compare a consensus-based timestamp oracle, the TiDB placement driver, to the timestamp oracle as a service with lots of different tests and scenarios and measurements. I'm curious, the paper doesn't assume timestamps are integers, but it seems like that's a useful piece of information if you always knew by how much a timestamp must increment. If it always has to go from 5 to 6, if it can't go to 5.5, that seems like maybe you can make the fault tolerant algorithm a little bit more efficient when during a partition, if it knows that. I'm not sure. But in general, I really like this paper. This is new to me, but it's got the flavor of classic distributed systems protocols, and it's really quite well explained if you give it the time. And that is the conclusion of my presentation. Thank you.